When you think about it, a health bar is just a way to represent some numbers. The real challenge is keeping the UI in sync with those numbers. In this video, we'll solve that using UI Toolkit's runtime data binding. Let's start with the traditional approach and the problem with it. Say you have a player data object that stores your data, like health, and a UI that displays it, the health bar. A common way to connect the two is the model view presenter architecture. You introduce a small mono behavior or script that acts as a relay between the model, your data, and the view, your UI. This middle layer listens for changes, responds to input, and keeps everything in sync. All of this works, but it comes with a cost. Here's the kind of code you might write in a presenter. To update the UI, you'd manually set the player name, format health values into a string, update the progress bar, and then maybe change the color based on health. You'd also need some kind of event or update loop to keep everything in sync. This quickly adds up. Every new UI means more of this logic to keep the data and the user interface up to date. Runtime data binding solves this by keeping the UI connected to the data automatically. Instead of manually pushing through updates, you define the connection once, and then you let the system handle the rest. Here we replace the presenter with runtime data binding. The model remains the same, it's still the source of your data. The view is still your UI, but now the connection between them is handled by the binding system. The view just declares what it needs, the model provides the data, and the binding system keeps them both in sync. Runtime data binding for UI Toolkit was first introduced in Unity 6. To use it, import using unity.properties, and then mark your properties with the create property attribute. Under the hood, Unity generates a property bag so the binding system can discover those values at runtime, and that's what makes them available to the UI. We'll add the using unity.properties line to our model. So in this example, we're using a player data scriptable object. Technically, any C# object can act as a data source, but scriptable objects are convenient here because they're serialized assets. Their data shows up in the inspector, and you can preview and tweak values while building your UI in UI Builder. This player data class is pretty minimal. It stores just a few states that we'll need for the health bar: the player name, the current health, and the maximum health. There's no UI logic here, just data. For anything the UI actually needs, we expose a public property and then mark it with the create property attribute so it can be bound. And remember, we get that from the Unity properties namespace. We can prepare our properties anticipating what we'll need to show in the UI. For example, we might have a health percentage as a normalized value between 0 and 1. And for the label, we can pre-format the max health as a string so that the UI can display something like 75 out of 100 more easily. The important idea here is that we design and format the properties with the UI in mind. The UI doesn't know how health is calculated, it's simply reading these values from the data. Let's actually look at the view in UI Builder. This is our HealthBar UXML. We have a player name label, a current health label, a label for maximum health, a visual element representing the fill bar, and a couple of extra labels to show our health state. So we're visualizing the same data in a few ways. This file only defines our layout and styling. There's no gameplay logic here. At this stage, the UI doesn't know anything about players or health systems. It just describes how things should look. We won't see the UI update until we create the data binding. For this demo, we'll create a player data scriptable object as a data model, and then we'll fill it with sample values. And this gives the UI something to bind to. To connect everything, go back to the UXML in UI Builder, select the root element in your UXML, and then assign the data source. That links the data to the entire hierarchy, not just the root, but all child elements as well. And this is a static setup that we're defining once. In part 2, we'll connect this dynamically at runtime like you would in a real game. For now, one static data object is enough to demonstrate the basics on how the data bindings work. In UI Builder, each property can bind to the data source. Let's start with the player name label. We want to bind the text property so it displays the correct name. Open the ... extra options menu and choose Add Binding. The data source is already filled in and marked inherited. That means it comes from the root element. Select a data source path. UI Builder lists compatible members it can bind to, including both fields and properties. For runtime data binding, it's a good idea to limit what's in that list. Go back to the ScriptableObject and add the Don't Create Property attribute to the regular serialized fields you don't want exposed. That leaves only the properties you've explicitly marked with Create Property, and that makes the binding paths easier to work with. Choose Player Name from the decluttered dialog and then press Add Binding. As soon as you create the binding, the label text updates. And note the little icon that indicates the data binding is in place. The label text doesn't store the value itself, it simply depends on that property. Repeat the same process for current health. Add a binding, select a data path, choose the current health property, add binding. UI Toolkit will convert the integer to text automatically. For the text property of the maximum health, you can choose between the raw integer or the pre-formatted string. In this case, the formatted version includes the leading slash, so it displays as /100, and that's what we'll select. Now watch what happens when we change the values in the ScriptableObject. Adjust the player name or change the current health and maximum health. As those values change, the UI updates immediately, and that means that the runtime data binding is working. Without any additional code, your UI and data are connected. Now the next step is to bind the progress bar element to the current health as well, and this one works a little bit differently. In this demo, we're not using a built-in progress bar, just a plain visual element. It fills by changing its width, so we're binding to a style property instead of something like text. Because the width is a style value, we need to convert our health percentage into a style length, and we'll do that with a separate property on our data. In the player data ScriptableObject, import the UI elements namespace and then add this property. This converts the health percentage into a %base width that the UI can use. Now back in the UI builder, add a binding to the elements width property. For the data source path, select the current health progress and then create the binding. In play mode, when the current health changes, the width updates automatically and the bar fills or shrinks. At this point, you can start to see the pattern. Each UI element simply declares the data that it depends on using a data source path. UI Builder stores those bindings directly in the UXML. If you open the UXML file, you'll see the binding entries added to the elements. So this whole setup is created visually and interactively using UI Builder while the data stays in your model. If you look at the UXML, you'll also notice that each binding includes a binding mode. You've seen these in the inspector as well. Binding modes answer the question, which direction does the data flow? Edit one of the bindings to see the options. ToTarget pushes data from your source into your UI, and this is the most common option. ToSource sends changes from the UI back to the data, like typing into a text field. TwoWays does both, keeping the UI and data in sync, so think toggles or sliders. ToTarget once sets the value once and then stops updating. We could have, for instance, used that for the player name. For most UI displays, like this HealthBar itself, you'll use ToTarget. So now we know what data to read and how it flows. The next question is, how should that data look? And that's where converters come in. For example, we don't want to show a raw value like 0.75 on the HealthBar. Instead, we'll convert it into something more readable, like 75%. We can also use that same value to drive other parts of the UI. In this example, the health percentage becomes a status label, full, mid, low, or critical, and also maps to a color for the health bar. So one piece of data can drive multiple parts of the UI. To do this, we create a static converter class and then register a few converter groups. Each group takes the same source value, the health percentage in this case, and then transforms it for a different use. One formats it as a percentage text, another turns it into a status string, and one maps it to a color. Each converter defines a name and the function that it calls to transform the data. We then register these groups so that the binding system can use them. Each group is added to a global registry, and then we call the static methods from a central register method that we define at the top. Register runs automatically in both the editor and at runtime. We use two attributes to make sure of this. InitializeOnLoad method makes them available in the UI builder, and runtime InitializeOnLoad method registers them again when the application starts. Once registered, these converter groups show up in the UI builder and can be assigned to bindings. Now let's apply them. For the health percentage label, the binding still points to health percentage. But in the advanced settings, we assign a converter using the converter ID. Select the health percent converter group. The value then displays as a string with a percent. We can then reuse that same data path for another label. This time, choose the health status converter, and now it shows full, mid, low, or critical. For the health bar, we bind the background color. Again, it uses the health percentage, but we'll disable the compatibility filter first to find that, and then we'll assign the health color converter in the advanced settings. And now the value is transformed into a style color. So all three elements use the same source data. Each binding just transforms it differently before it reaches the UI. Now we have a working health bar. Change values in the scriptable object, and the progress bar updates, the labels update, and the color changes automatically. To simulate gameplay, we've added a small tester script that adjusts the health through the UI buttons. Now, it doesn't matter where the change comes from, the scriptable object, gameplay code, or the UI itself, the result is the same. There's no update loop driving any of this. When the data changes, the bindings respond automatically. Converters then handle how that data is presented, so the logic stays separate from both the UI and the gameplay code. If you want to try this yourself, download the sample project linked in the description. In part 2 of this video, we'll create health bars dynamically and then assign data at runtime. Thanks for watching.